Historically, automotive safety was a one-dimensional problem. Engineers focused strictly on preventing random hardware faults and systematic design errors, governed by a single standard, ISO26262. The transition to software-defined vehicles and autonomous robotics changes the scope of the problem. When mechanical linkages are replaced by continuous digital networks, verifying hardware faults only covers a fraction of the total risk surface. Modern cyber-physical systems operate under the simultaneous demands of four disparate dimensions of safety. These are deterministic functional safety, active cybersecurity against malicious attacks, open-world sensor physics, and non-deterministic artificial intelligence. The engineering philosophies that govern these four domains naturally oppose each other. What makes a network secure can easily make it too slow to break in time. Evaluating these domains independently, passing them off to separate departments using isolated compliance checklists, leaves areas of the system where requirements are unmonitored or uncoordinated. In a complex architecture, an optimization in the cybersecurity layer can create conditions where the functional safety layer is unable to respond to a hazard. To resolve these cross-domain engineering conflicts, the industry requires a meta-framework known as an integrated assurance case. This approach shifts safety reviews away from stacks of static, fragmented compliance documents into a single, logically structured hierarchy of evidence. Assessing this unified architecture requires a joint confirmation review, where evaluators interrogate the requirements of all four standards simultaneously. To see why this framework is mandatory, we have to look at exactly how these distinct safety domains collide on the actual hardware. Engineering rigor requires mapping the exact physical and logical intersections where different international safety standards impose conflicting requirements. The clearest architectural conflict occurs between ISO 26262 functional safety and ISO 21434 cybersecurity. Functional safety operates on a fail operational mandate. If a component breaks, the system must maintain availability long enough to guide the vehicle to a minimum risk condition, like pulling over to the shoulder. Cybersecurity relies on a fail-secure philosophy. If a threat is detected, the immediate protocol is to isolate and sever the compromised network nodes to prevent an attack from spreading. Consider a scenario where a malicious network payload breaches an external infotainment node and attempts lateral movement toward the critical brake-by-wire system. The system controller faces an impossible dilemma: maintain network communication to ensure the driver retains braking control, or instantly quarantine the network to stop the hack. This diagram illustrates the strict functional safety metric governing this dilemma, the fault-tolerant time interval, or FTTI. FTTI is the physical maximum time allowed from the moment a sensor detects a hazard to the moment the brakes physically actuate to prevent a collision. To prevent hackers from spoofing those braking signals, cybersecurity standards require the use of message authentication codes to cryptographically verify the data payload. Generating and verifying these complex codes drastically increases the calculation time required by the microcontroller. If engineers prioritize maximum cybersecurity, the resulting network latency causes the vehicle to miss its FTTI deadline. In a cyber-physical system, applying digital security without coordinating with the functional safety layer creates a direct physical hazard. We also have to account for situations where the hardware operates perfectly and the network is secure, but the physical environment restricts the system's performance. This is the domain of ISO 21448, known as SOTIF, or the safety of the intended functionality. It addresses the physical limits of sensors operating in an unpredictable open world. Cameras, LiDAR, and radar all possess inherent limitations based on physics, regardless of how elegantly the underlying software is written. A camera can be completely blinded by intense sunlight lens flares, and radar can create false ghost targets from radio reflections inside metal tunnels. These limitations define the Operational Design Domain, or ODD. This establishes the strict geographical, climatic, and speed boundaries where the vehicle is certified to operate. SOTIF validation requires engineers to intentionally inject physical perturbations into closed-loop simulations to map the exact boundaries of that ODD. The goal is to prove the vehicle can recognize an OD exit in real time and safely transition control to the driver or initiate a minimal-risk parking maneuver, rather than executing an emergency stop in moving traffic. Open-world safety relies on statistically proving the vehicle understands its own physical limitations and knows exactly when to surrender control. The final architectural layer involves artificial intelligence perception models, governed by ISO Pass 8800. As we can see in this comparison, traditional automotive software is built on logic that produces a single, guaranteed output. Machine learning neural networks process data probabilistically, relying on pattern recognition to generate inferences. This introduces the vulnerability of distributional shift. If an AI enters an environment slightly different from its training data, it can produce unpredictable outputs. Because no deep learning model is 100% accurate across all possible scenarios, a different approach to safety is required. Under ISO PAS 8800, safety compliance is achieved through containment, not mathematical perfection. The probabilistic outputs of the AI must be physically bounded and cross-checked by traditional deterministic C++ safe state monitors before any command is sent to the steering or braking actuators. This brings in Clause 15, the toolchain risk. If the C++ compiler used to build the safe state monitor has a memory leak, the logic designed to contain the AI becomes as unreliable as the model it is supposed to monitor. A single unpatched flaw in traditional software testing can render a multi-billion parameter AI model ineffective in a real-world scenario. The safety of cutting-edge, non-deterministic artificial intelligence ultimately relies on the execution of deterministic software engineering. We now have FTTI latency conflicts, open-world physical limits, and non-deterministic AI vulnerabilities all overlapping simultaneously within the same vehicle. Treating these four standards as separate checklists overlooks the functional dependencies between them, often leaving systemic risks unaddressed. This hierarchical logic tree illustrates the structural solution, Goal Structuring Notation, or GSN. GSN creates a top-down deductive tree that forces engineers to logically connect every disparate safety standard to one unified global safety goal. The most crucial mechanism within the structure is the assumed guarantee contract, the lateral rules that bind the separate branches together. These lateral contracts prove that fixing a vulnerability in one domain won't violate the limits of another. This digital thread acts as a living feedback loop, where discovering a new AI bias immediately forces engineers to recalculate and adjust the physical ODD limits. True safety in the era of autonomous systems isn't found in mitigating individual risks, but in rigorously governing the spaces where those disparate risks interact.